This is the Krembil Discovery Tower. Hi, I'm Jay Ingram. There's an incredible amount of research going on here to try and find cures for conditions such as arthritis, blindness, even Alzheimer's. Today, I'm going to introduce you to three remarkable researchers. First, Dr. Mohit Kapoor. In Dr. Kapoor's lab, the pursuit of a cure began with understanding this disease. It afflicts more than 4 million Canadians and counting.
This is a knee joint.
Yep.
On the edges of this bone, you have this specialized tissue called cartilage. And as you age or in response to any injury or any kind of biological stress, you start to get degeneration of the cartilage. As the degeneration of cartilage takes place, the space between the joints decreases. As a result, you have loss of motion, as well as you have restriction in the joint function. You have pain, inflammation.
As sufferers of osteoarthritis discover, the disease progresses unnoticed and is practically impossible to diagnose early on.
Now, let me show you an osteoarthritic joint cartilage.
Dr. Kapoor wondered if he could change that, come up with a way of diagnosing it early. And to do that, he began the search for what causes the cartilage to degenerate.
So we've done a massive screening and identified 2 biological markers which actually can play an active role in destroying your joints. If you detect the levels of these in the cartilage, they can also tell you what stage of osteoarthritis you have.
You mean the more of these products there are, the further on you are in the arthritis?
Absolutely.
The discovery by Dr. Kapoor and his team of the 2 biological markers that destroy cartilage is a world first. Now they're working on a simple blood test to measure the presence of those 2 markers in the body.
If we can detect these in the patient bloods, we can now then devise a simple blood test which could then tell us what is the stage of osteoarthritis one has. The second thing is, can we actually block these biological markers? By blocking these biological markers, you will be able to stop inflammation, pain, as well as reduce the dying of the cells in your cartilage.
Developing a blocker that stops the destruction of cartilage and halts osteoarthritis is the dream. But Dr. Kapoor knows discovery is a painstaking process. So there's the pressure to come up with a cure, or at least an effective treatment, but there's also the fact that you know very well that science takes a long time. So how do you personally deal with those tensions?
Everybody has a passion, and my passion is finding a cure for osteoarthritis. And this is the sole reason why I'm working in this field.
Next, I'm headed to the Krembil Tower's 8th floor to see Dr. Valerie Wallace. We begin with a crash course on the diseases that cause blindness in more than 1 million Canadians. So, Valerie, can you walk me through this?
So the part of the eye that we're trying to fix is the retina. The retina sits at the back of your eye, and it's actually part of your brain. And it's connected to the rest of your brain by a nerve.
The optic nerve.
The optic nerve, that's right. The part of the eye that we're interested in are these cells at the back of the eye called the cones. And they allow you to see color and to do things that are fine detail, like read. And what happens in diseases like age-related macular degeneration, as well as the late stages of retinitis pigmentosa, is those cells die. And once they die, you can't see.
Just in the center, or?
Yeah, so you lose your central vision.
So, this is your issue that you're trying to tackle. How are you trying to do that?
So the one remarkable thing is that once these cells die, they leave the rest of the retina intact. So these are the cells that form the rest of the circuit that connects you to your brain. So it's a very simple idea.
So all is not lost?
All is not completely lost. So the idea we've had is, could we put healthy cells back in to that empty space? Would they connect and restore that circuit so that you could see? And that's exactly what we're doing.
Injecting healthy cone cells to restore vision is pioneering research and presents major challenges. How do you inject the cells? How do you keep track of them once they're injected? And finally, and most important, will the cells take? Can they restore vision?
So we're at the stage where we can get subretinal delivery and we can get them to survive. Not lots of cells, just a few thousands of cells, but they survive. And we were really surprised to find out that actually they're starting to look like they're maturing. And
Wow.
yeah, so we're at the stage now where we would like to test vision. Then once we have proof of concept, then it's worth investing in looking at, can human cones do this?
This process has been a painstaking journey and passion for Dr. Wallace and her team, one that began more than 4 years ago. You know, there's a certain tension, I get the feeling that it does take years to move. You're moving forward all the time, but it's years, and yet there's this urgency to find a cure. So how do you deal with that?
So the urgency is also what motivates us to do this work. Of course, I'm hoping we find a cure, but I do think we are still very early days in making discoveries. To be a really good explorer, do it really well, work with great people, talk to great scientists, eventually all of that put together is going to lead to better treatments.
Our final stop is the 4th floor at Krembil, the lab of Dr. Dawn Weaver. Alzheimer's is one of the fastest growing diseases in the world. Today, more than 700,000 Canadians have Alzheimer's. That number is expected to double over the next 15 years. Dr. Weaver embarked on his research journey to cure Alzheimer's more than 20 years ago. And like his colleagues, he began with a simple question: how does the disease start?
Alzheimer's disease is a protein misfolding disease. There's two proteins, one called beta amyloid, one called tau, and they both clump. And when they clump, they destroy brain cells. So what we are endeavoring to do is to come up with one molecule, one drug, that will prevent the clumping of both beta amyloid and tau.
Even though those are very different substances?
Even though those are very different substances. So we think that we have identified something that we call the common misfolding shape that really enables both beta amyloid and tau to misfold, and that we are honing in on that abnormal shape to try to enable us to design drugs.
So what exactly is entailed by honing in?
So using computer modeling, we've actually modeled the shapes that are abnormal in both beta amyloid and tau. With that shape, we have screened 11.8 million compounds against it in the computer, and then identified some leads, and then subsequent to that, we've been synthesizing them or preparing them and making them and putting them through a wide variety of different biological tests.
So once the team has a compound they think shows promise, it goes to the organic chemists. But of those 11.8 million compounds, only a few hundred have made it to the advanced testing stage. What makes a candidate?
Every drug is a molecule, but not every molecule is a drug. So what we're looking for is a compound that has what it takes to go from gums to brain. And so when you swallow it, can it survive the gut? Can it go through the liver? Can it make it to the brain? And not only that, it should also have the ability to bind to beta amyloid and tau and to prevent them from misfolding. Not exactly an easy task, so we got to screen a whole bunch of compounds to do that. We have the standard joke that it's methyl ethyl propylbutyl, but you know.
And there are other factors when choosing what compounds should be converted into a test drug. Ensuring the end product is safe and non-toxic, that it's affordable, and finally, that it works.
And now we're doing the final touches to try to make these more applicable to humans. And by the first quarter of 2017, we hope to have declared a compound that we want to take into people.
There's a definite urgency to come up with medication for Alzheimer's.
Certainly is, yes.
But as you've indicated, the process is not fast.
No, it's not.
So how do you deal with those opposing tensions?
It is a big issue, and it's a business issue as well, because you have people investing in these compounds who want to see you move quickly. On the other hand, you have to get the right compound. We always try to make our molecules safe and as effective as we can. If that takes an extra 6 months, it takes an extra 6 months. We'll be very happy if we are able to come up with a useful drug.
I would say the entire world would be happy.
It's clear these Krembil researchers feel the urgency to discover a cure. And yet, every day, they must reconcile that desire with the truth about science. It's painstaking, precise, and rigorous. Most of all, it requires time, lots of it. To be relentless in their pursuit day in and day out takes special people. These are 3 of more than 160 amazing Krembil researchers who possess those qualities. For Toronto General Western Hospital Foundation, I'm Jay Ingram.